let's start up. Here's our sequence. I'm going to tell you about t-distributions. We kind of know what's coming, that for the normal model, where this thing right here is just, you know, your Bayesian posterior, and your x's are coming from, so I'll say this, cap x is a collection of x's, xn of them, and then each one of those xi is coming IID from a normal distribution. I'm going to write that down like this. Normal mu sigma squared. And I've reparameterized everything in sigma squared, and I just inverted that thing, and I call it the precision parameter. So we already know this thing's going to be t. So we have to just understand what t's look like. So I'll walk you through that. And then I want to move into some forecasting. And I've always kind of thought about, you know, I've always thought this was kind of a fascinating realization. I'm not sure when I finally made this realization, but at some point this was like fundamental to me. And it was, how do we predict something? If everything were IID, you're tempted to think that the past can't tell you about the future, because all the realizations are independent of each other. And so Bayesian is really thinking this, that this is my collection of data that you've observed. This is what you get to see, observations. And you want to put a probability distribution on something in the future. So this is going to be a future draw. That's my future. Bayesian is uncertain about the future, so they're going to condition on what you know. And then they're going to try to put a probability distribution on x tilde. And there's always this misunderstanding about what it means to be IID. Everything is independent. Data itself is not independent. It's independent given model in model parameters. So in a forecast, what you're really doing is you're learning what the model parameters look like, and you're integrating them out of the equation. So you're learning the model. And so if I knew what the model looked like, if I knew what theta was in general, I would just take a draw from it. But what we don't know is theta. So we need to get rid of it in this equation. Again, anytime we want to get rid of a parameter in Bayesian land, we integrate over it. That's what we always do. We don't just plug something in for it. We marginalize it away. We average it away. We average it with respect to the posterior distribution. And so you can be thinking about, how do I get this forecasting distribution in general? But the key is you get the posterior, we weight everything by the posterior, and we integrate it away. You may be thinking about that. I'll be asking you about this towards the end of class. Let's just finish up with this problem, learn more about t-distributions. So I'm just going to tell you what a t-density looks like. This is just kind of a side into learn a new distribution. So t-distributions. We kind of saw this last time, but I'm just going to review everything. So let me just tell you what they look like. So if something were t, I'm going to say my random variable is z. And I always do this, so don't be confused. A lot of times people say, oh, z is normal. That's my standard normal thing. Every time I just inject a new random variable on you, I usually call it t. So f t is my random variable. There's three parameters that underlie a t-distribution. There's the degrees of freedom. And I'll explain this a little bit geometrically, but I'll also explain it algebraically. So I think a lot of people get hung up in the geometric interpretation, and they're like, what is this elusive thing? It's a parameter in your model. That's all there is to it. So there's the center, or the location, i.e. the center. Oftentimes you're thinking of something like a mean. T-distributions don't always have means. If they do have means, it is that parameter. So a T1 has too heavy of tails, for there to be a mean in that distribution. There is a center of that distribution, but there isn't an expectation. And you can convince yourself of that a little bit later. T2s do have means, they don't have variances. So there's another parameter, and it's called the scale parameter. Sometimes I might throw a sigma squared on there or a sigma, but it acts and it feels like sigma in a normal distribution. If the distribution does have a standard deviation, this is it. And if it had a variance, it's sigma squared. So T1s don't have means and they don't have variances. T2s, I'm saying this parameter. When I say a T1, I mean with 1 degree of freedom. So when the degree of freedom is 1, no mean. But if the degree of freedom is 1.0001, and it can be anything that's positive, you might not be used to playing around with it as a continuous parameter. But if it's 1.000001, it will have a mean. If your degrees of freedom are not greater than 2, you won't have a variance, but you'll still have a scale parameter. So we just need to be a little bit careful with what the interpretation of these things are. And these look like this. So I'll just write down what the kernel of the distribution looks like first. There's going to be a normalizing constant. We'll fill that in a second. Normalizer, but then there's the kernel. And it's all the stuff that has to do with the random variable. In our case, we're calling that z. So this is going to look like 1 plus z minus the center over the degree of freedom over sigma squared. And then it's powered up to the 1 plus degree of freedom over 2. And that's what it looks like. There's a square right here. That thing is square. Okay, so that's what it looks like. In this thing, you can kind of see that this looks like it's centered at mu. So I'm just thinking about this as a linear shift. It's just shifting z. So it's just your centering parameter. And we can see the scale term pop up. If you look at something like Casella and Berger, they'll show you this distribution. So, let me write down what the normalizing constant looks like. It's a gamma function, mu plus 1 over 2. Gamma function, mu over 2. And then there's this thing, square root of pi, that's pretty cool. And then there's nu, your degree of freedom. And there's also sigma squared floating around here. And it'll look like this. Sigma will be out in front. So my standard, the thing in the square root is just that stuff. If you want to tuck sigma squared under there, that's fine. So the standard T. So this means mu is equal to 0 and sigma is equal to 1. It's just this equation, but you just plug those things in. So it looks like this. 1 plus z squared over degree of freedom minus degree of freedom plus 1 over 2. Gamma functions are still there over gamma. And this has my 1 over square root pi times nu. So you can see that this is a location scale thing. If I ended up just taking this and shifting it by mu, it'd pop up here. And so if I considered a transform where I subtracted off mu and divided by sigma, everything would just pop up here. Keep in mind, this little term pops up when you do that transformation. So that's the scale parameter. So usually when you standardize something, you just take whatever it was here. I'll take z minus mu divided by sigma. And they'll pop up here squared, and that sigma will get squared. So if you're thinking about standard forms of something, subtract off the center, so you center it at 0, and divide out my scale, and that always pops up here. You'll remember the priors that we used for understanding scale parameters. They look like 1 over sigma. 1 over sigma is the parameterization for a typical scale prior. 1 over phi is the 1 for precision. 1 over sigma squared is the 1 for variance. Danielle.
Should I be phi over 2 in the denominator? Is that called a
You want a 2 right here?
No, in the gamma function.
Oh, yeah, this one is over 2. Yeah, thanks. It's because I never use them. I always forget about them. If we were doing inference on new, we would need that there. And I would have made a huge error. So, okay, good. So that's what a t-distribution looks like. This parameter right here, it's determining the tail heaviness of the distribution. So these things look like this. They're bells, but they're different bells than the bell I normally am drawing. So it has some scale, and that determines how diffuse the distribution is. But this new parameter, the degree of freedom, is measuring how thick the tail is. So what this tail behavior is right here. So if nu is very small, this tail is very fat, very thick. So it controls tail behavior. And a lot of times I'm really interested in tail behavior. So in problems that we don't know a lot about, oftentimes figuring out what the tail behavior is extremely important. Normal distributions come down faster than this. They come down exponentially fast. And in fact, exponentially with quadratic in there. That's extremely quick that it comes down. A lot of times people try to assume normality, and they'll be shocked every once in a while. They get samples, they're all around here, and then every once in a while you get a sample way down here. So I'll have you simulating from Cauchy's in this class because it's kind of fascinating. So Cauchy distributions are t's with 1 degree of freedom. So I'll just write that down. Nu is equal to 1. So these are very fat tails. Some people say they're heavy tails. So I don't know if I've ever heard anybody say they're thick tails before today, but I guess that would be a description as well. And it kind of controls the uncertainty of everything. And so I think it's enough just to think about that. We'll talk a little bit about the geometric interpretation, but it kind of comes from how many things do you need to know before you can figure out the answer to the problem. So here's an example of this kind of in a more geometric sense, and we'll turn to this after we figure out what this integral is that we're trying to solve. But if I have one piece of chalk, 2 hands, which I do right now, and I hide the piece of chalk in one of the hands, and I tell you it's in one of the hands, not in both of the hands, not in 0 of the hands, I might ask you, how many hands do you need me to open before you know where the chalk is? It's 1. So which hand would you like to see? So that's where the chalk is, and there's no chalk. But if Warren had asked for this hand, he would have known where the chalk is. So this problem has 1 degree of freedom, but it's kind of 2-dimensional. So we'll come back to that later. So this is our t-distribution, and we're going to be aiming for recognizing this piece of it in the problem that we're solving.
Well, aren't degrees of freedom dimensions minus 1, number of dimensions minus 1?
It depends on the problem. So in like a contingency table problem, it depends on what you know. You know the margins. So it might be the columns minus 1 times the row minus 1, depending on the problem that you're solving. It could be the number of dimensions minus 1. For this problem, it turns out it's n minus 1. But it depends on the problem. So it's not always n minus 1. It's sometimes something different. So that sort of Test of independence, the chi-square test, that's a counterexample to that. So it depends on what you know. It has to do with the constraints of the problem.
Are degrees of freedom all integers, or can
They can be anything.
from 0 to infinity, or?
Yeah, from something positive. Just remove the 0.
Okay.
Yeah, so it can be something else. You might not be used to that. So I usually, when I do modeling, I use nu is equal to 1, because I know a lot about Cauchy distributions. I'm just trying to express a lot of uncertainty. But technically speaking, it can be anything. Still a distribution. Jenny.
Exercise sigma, it said square.
Sigma's outside of the square root, the way that I wrote it. If I put it inside out of the square. So just like a normal, it pops up just like that. And the nu is acting as some sort of a scale as well, but it's not scaling. It's doing something slightly different than all of that. It shows up in this exponent right here. So it appears a little bit different than the scale, but you can see that there's kind of this interaction between these two things. So it's hard to tease them apart. So if you didn't have much data, it might be hard to learn it. Okay. We'll see that in the context of this problem, how degrees of freedom comes into play. But you're just thinking of it as a parameter that controls the thickness of the scale, which is different from variance. So there's this third parameter that determines this distribution. I really like these distributions. And I'll have you playing around with these distributions a lot in class. So I'll have you do things like heavy-tailed regressions in a couple weeks' time. The new homework that will be coming out, if you haven't turned in your homework yet, just slide it under my door. If you forgot to print it or something like that, slide it on my door today. I'll have a new homework posted and we'll have these returned to you soon. But I'll be building you up to doing Cauchy regressions. Okay. So we're going to recognize this kernel. So this is something you need to know in this class. I do not believe there's anywhere where you need to know this. If you're trying to open up stuff, your memory banks, and free up other pieces of memory, make sure you memorize this. If you want to omit something, you can omit that. But keep recognizing the kernels of distributions and what their parameters look like. Okay, so back to this problem. Back to finding pi mu, given x. And we wrote this down at the end of class, but we can do this again. It's just basically recognizing what a gamma distribution looks like. So we're going to write this thing down. We're going to integrate over our precision parameter, given x, where these are n data points from a normal distribution. I'm just going to start writing everything in terms of phi. So then I'm going to integrate over phi. How did we find this? We wrote it up to proportionality because we're just going to be looking for the kernel of the distribution. We just need to hold on to all the stuff that depends on phis, because I'm going to integrate over it. Depends on mu, because that's my random variable, and I need to connect it to the x's. So that comes through the likelihood function. So that's just going to look like this. Product 1 to n. This will look like phi to the 1/2, e to the minus 1/2. I'll write it like this. E to the minus phi, xi's minus mu squared over 2. And then I have my prior. And it looks like this. So if you'll allow me to simplify this, I can recognize what the kernel of the integram looks like. And because I know all about gamma distributions, I know what its normalizing constant is, I can solve this integral pretty easily. Solve it, because I recognize the pattern. So 0 to infinity, I guess we'll have this equal. But just keep in mind, I wrote down proportionality once. I don't regain equality in the original problem. So this looks like phi to the n over 2 minus 1. E to the minus phi sum of the xi's minus mu squared over 2 dphi. So this looks like a gamma. It's got a couple parameters. I usually just build in some notation and I nickname those things. So alpha twiddle is n over 2. That's where I recognize it. It's always in front of the minus 1 if I have everything parameterized according to my convention. And this is beta twiddle. It's the thing that sits in the exponent. So this is sum of the xi's minus mu squared over 2. I know what this thing integrates to because I know the normalizing constant to a gamma. So this whole thing will integrate to this. Pi mu given x is going to look like the inverse of the normalizing constant. I'll write it down after proportionality. Saves me a lot of work that I really can't do anyway because this whole thing involves gamma functions. So you're not really writing anything down other than an integral when you express a gamma function. And so this will look like gamma alpha twiddle over beta twiddle alpha twiddle inverse. This is my inverse normalizing constant. For gamma. Eventually, this is all going to become automatic. Keep in mind, alpha twiddle is just n over 2. We know what n is in the problem. So gamma function of n over 2 is just a number. We've already written everything up to proportionality, so I can get rid of that. But the beta twiddle has all our x's and our mu in there, our random variables. We can't get rid of that. So this whole thing will be proportional to sum of the xi's minus mu squared. There is a divide by 2 in here. I guess we can hold on to it. And this is going to look like to the minus n over 2. That's my alpha twiddle right there. So our posterior is proportional to this. And that's where we left off last time. And so now we have to recognize this as a T-distribution. And so how do you do this? You do it once and you remember how you did it. But there are a couple of little clues as to what you do. So let me just rewrite this. I can get rid of the 2 because it's up to proportionality. That's not helping me at all. Xi's minus mu squared to the minus n over 2. I just leave that thing hanging out right here. So again, what we're looking for is some form like this. So I need a 1 in there. I need to shift this thing over and play around with this until it looks like that. Let me just ask a question. Where is this thing centered? How can you tell?
Mu.
It's not centered in mu. Mu is the random variable. So again, this sort of flip thing that we're all getting used to. Soon we should be used to it. It's not centered at mu because that's the random variable. Where's it centered? It has something to do with the data. The data is telling us about the centering.
X bar.
X bar, how can you tell? It's just something you know, or is there a giveaway here? In terms of quadratic forms, when you have your data, subtracting out your random variable, if that thing is quadratic in there, you're always thinking it's centered at X bar. And you can check that. So if I wanted to know some problem like this, this is just a side. If I just had a problem that looks like this, xi minus f, some function right here, squared, I equals 1 to n, I might ask, what's the max of this thing, or where is it maximized? And so how would I figure this out? So the standard sort of calculus problem. So if f was a continuous random variable, it could be any number on the continuum, I would know how to answer this question. You could divide by n, it won't change anything. And I could power this up. But powering something up doesn't change where it's centered. It changes the scale of it. So it changes more than the scale, but it changes how peaky it is. So if I take something and I raise it to a very, very small positive number, it flattens it. Now if I raise something to a very, very big number, it makes it peakier. You can verify that to yourself. If you know about MCMC and parallel tempering, that's the schema that's used. They basically flatten things out by powering things up. More of that sort of stuff later. So how would I do this? I take a derivative with respect to f, and I would solve for 0. And when I solve for 0, or I solve for f, I would probably call it something different. So I don't like to do this in one step, but you can just do this. This is just the chain rule. The square comes down. So pretty easy derivative. And then I've got this minus f. So minus 1 shows up in the chain rule. So this is going to look like sum of the xi's minus f. 2 minus sign if you would like. That's the chain rule coming out. Derivative of f, negative f. I'm going to set this whole thing equal to 0. Right here, and I'm going to solve for f. I'm going to throw an f, this on top. So this isn't too hard to figure out. Get rid of that. Solve for f. What's f? Can you do it in one step? I bring it over to this side.
Sum of xi and minus.
Got it. This is x bar. A lot of times I'll throw an n on there just to denote that it has something to do with n. So if I'm taking limits, I can see something happening there. But this is just going to be some of the xi's minus nf. Bring it over to the other side, divide by the n. Bada bing, bada boom. So now every time you see something that is a sum of quadratics, you're thinking it's centered at x bar. That happens here as well. Forget about that. So this centers at x bar. So I'm going to do my magic trick that everybody always says, how do you know to do that? I know because of this. That quadratics, when I take a sum over it, it's centered at an arithmetic mean. And so since I know that, I'm going to shove it into the problem in a funny form. So I'm going to subtract off x bar, and I'm going to add in x bar. So we just get rid of x bar right here, and I'll just add in an x bar plus this one. I'll subtract that out. So add x bar, subtract x bar.
Shouldn't that be a plus? Bar plus mu.
Yes, I have that negative sign plugged in. Yeah, absolutely. So add x bar, subtract x bar. So this is just a funny form of 0 that I put in here. This whole thing is being squared. You get used to this real quick. You take an inference class, you see the same move being made like 17 times. We get it too in this class. So now I'm just going to expand the quadratic. I try to remember this minus n over 2, so I write it down first. And I'm just going to expand this thing out. I goes from 1 to n. And pay attention to this step because I'm going to ask you to do this in high dimensions in a future homework in matrix form. So there's a multivariate form of the t. And I'm going to be asking you to do something just like this, and the moves are very, very similar. I'll give you some hints as we get closer to that problem. So this is just xi minus x bar squared, that first one. I've got the cross term, so this is going to be, give myself just a little bit more room. This is going to be plus 2 times xi minus x bar minus mu. And then I've got this term, squared. X bar minus mu squared. And this is just closing that one that I still need to take the sum over. So this is sum. I goes from 1 to n, xi minus x bar. And you're thinking something when you see this term. What do you think of when you glance at this first term that we've written down? Yeah, it has something to do with variance. That's right. So when I drag the sum across this is constant in the sum. So I'll just show you this once. Everybody knows what this term turns into. You drag the sum across everything, it turns to 0. Just keep this thing up here. 1 plus z minus mu over nu sigma squared. Close that out. So that's our kernel that we're aiming for. Normalizing constant, I don't need to know anything about. So sum of some constant, if you'd like, I'll write down which constant that is. That's just x bar minus mu. Xi is minus x bar. What's this? It's 0. So this is just equal to sum of the xi's minus nx bar. What's nx bar? Sum of the xi's. That's 0. So this term disappears. And that will always happen when you make this move. It's very convenient. In this one, it's summed up n times. This is plus n times x bar minus mu squared minus n over 2. And we can see that now mu, where it appears, it's being shifted by x bar. And so we've reaffirmed something we already knew, which is why we introduced the x bar, that this was going to be centered at x bar. And we see it right here because mu is being subtracted from x bar. If you like writing your random variables on the left, like I always do, you can flip that around because everything is squared. And so my random variable's on the left over here. So we can spin those around. So we want a 1 over where this thing is. You've got to get rid of this and turn it into a 1. And divide by that same thing, and I multiply out here. So I factorize it out. Let's just do that.
So where
These are the sort of moves that I make really quick sometimes, and everybody's like, how did you factorize it out? So I'll be really pedantic, please.
Where did the n come from?
This is being summed up. All of these terms are being summed by this right here. This is a constant.
Oh, you pulled it outside of the sum.
Yeah, that's right. So it's in, yeah, exactly. So now this is the only thing inside of my sum. Sorry about that. Hard to see. Yeah, so now the sum's been acted on everything. So now what I'm going to do is I'm just going to factorize this thing out. Usually when I'm doing this on paper, I don't even write this part down, I just write proportionality. You'll do that after you see this one step being done right here. So this is going to be squared right here. I goes from 1 to n times minus n over 2. This is going to be that same term, xi minus x bar squared divided by sum of the xi's minus x bar squared. I've factorized this out, so I need to raise it to the same power. And this is going to be plus n x bar minus mu squared divided by sum of the xi's minus x bar squared. Label all my indices. So these are equal to each other. They're the same things. I've just factorized that out, and I've written one in a very, very funny way. So now I'm going to get rid of this thing. Has nothing to do with mu, my random variable. All the x's are known. They're constants. So the Bayesian posterior has all the x's constant. So I'm going to get rid of that and write this thing up to proportionality, and I'll rename this 1. In the multivariate form, this will be an identity matrix. You need to be careful you're not dividing by anything with a matrix. So be careful on the multivariate extension to this. So this will look like this. So remember what we're working on. We're working on this problem, and we've just written down this is proportional to 1 plus, I'll spin those things around, mu minus x bar squared minus n over 2. And this is going to be, there's an n still up here, upstairs. And then I have the sum of the squared residuals from x bar. We're almost there. This almost looks like this, except I don't have the plus 1 in here, so I want to shove it in, and I need that degree of freedom. So what I first look for is, what is the degree of freedom? Where do I recognize it? I recognize it up at the exponent. I don't try to recognize it downstairs because I've got sigma being multiplied right in there. It's hard to identify. So first thing I do is minus n over 2. I want my plus 1, so I'm going to subtract 1 plus 1 right there. As you guys already knew, the degree of freedom in this problem is n minus 1. So this is the degree of freedom. So I need to throw that degree of freedom down here because it's sitting right there. So if I throw it down here, I need to divide by it as well. So I'm going to multiply and I'm going to divide all at once. So this is mu minus x bar squared. I'm going to drag this n downstairs as well. So I'll throw it down there. This is going to look like sum of the xi's minus x bar, divide by n minus 1, my degree of freedom, so that I can multiply by n minus 1, my degree of freedom, right here. And I also have this divided by n. So that's this n right here. And we're done. Now we just have to recognize. So this is also the degree of freedom. I threw it in there because I know it needs to be there. So I divided it out, and then I drop down this n. This right here is s squared. And we talked about that last time. So that's our typical estimator of variance, if variance existed.
Why is the divide by n not part of it?
Because this is asymptotically, we reduce the variability in all of this. So my scale parameter right here, I'm just circling that part. This part right here goes here, divide by n. So that whole parameter, which is acting as
I got you.
scaling
X squared versus sigma squared.
Yeah. And it kind of makes sense because as n gets bigger and bigger, our uncertainty shrinks. And that's what that n is doing. So n minus 1 appears right there. This is the unbiased estimator of sigma. In our problem, sigma squared. In our problem, we have this extra n because we have more data points coming in. And so we recognize this whole thing as a t. It's centered in x bar. It's got degree of freedom n minus 1, and it's got scaling parameter s squared over n. Usually people take the square root and call that the scale, but because we're pretty loose, I usually call that the scale. Be very careful when you go to R as to what is called the scale. And if they think you're inputting it, either being squared out or square rooted or whatever the case may be, you have to follow their rule. So this is a t. It's a t density function. Centered at x bar, it has degree of freedom, is n minus 1. Center, its location is x bar, sum of the xi's over n, and the scale. I'll just be a little bit loose about this. This is sum of the xi's minus x bar squared divided by n. I'm just going to leave it for right now. And the degree of freedom is just controlling the tail thickness. I think that's good enough. So some of you know a little bit more about this, and it's like makes this thing unbiased. If you knew what mu was, then you would divide by n instead of n minus 1, and that would be unbiased. But you're using your data twice to estimate the location, and that's where that extra degree of freedom falls out in a geometric sense. I don't know if that helps you guys. It doesn't help me. Daniel?
So I was thinking the scale should be s squared over n.
It is s squared over n. Sorry about that. Divide by n. So that's s squared over n. Yeah, absolutely. So the scale is being reduced as we see more and more data. That's a good thing. Who has questions about this? It's really just a lot of algebra. Recognizing the distribution, understanding what you're doing. We're trying to do a unconditional inference on the mean. How does a Bayesian do it? They integrate over the variance right here. So one thing to notice is that a t-distribution is a normal scale mixture model with a gamma. So you're mixing over the gamma. So what integral did we just solve? We took a normal distribution, effectively, and we integrated over phi, the inverse of sigma squared. So I'll just say this is a fact, just to make another connection for you. T's are scale mixtures. That's a new word for us. Of normals, where the mixture is a mixing over gammas. Let me just rewrite that. So if f z given mu and phi, if this was normally distributed, and phi is a gamma, I have a homework problem for you where you can work through this. Then, integral f z given mu and phi, pi phi, d phi, this is going to be a t distribution. Now there's a little bit missing in all of this. 0 to infinity. Which gamma is this? And so in your homework, I'm going to ask you this question. What parameters do I cut here for this to be a gamma with new degrees of freedom? For it to be centered at mu, it's going to preserve the exact same center. And if you would like, I could end up writing sigma squared down here. And this would be with the scale parameter sigma squared. Sigma's the scale. I'll stop saying that eventually. So if I take this thing, it's going to be some gamma distribution, and I mix over the scaling parameter for a normal, I get a t back. And that's what we just did. So effectively, that's what we used. So remember, the likelihood function was all coming from the normal distribution stuff. So I plugged in what looked like the sampling distribution of a normal. So if I mix over the scale parameter, I get a t. These are called scale mixtures. So if this is a scale parameter right here, and I average it in some funky way, I get back this other distribution. That's what I do when I make distributions quite often. I start with distributions I want, and I mix over them in particular ways. And I get different behavior. So in your classical statistics class, or your inference class, you came up with an answer very, very similar to this. You think about it differently because this isn't the probability distribution for mu. The Bayesian gives you that interpretation. But you would do your inference off of this same thing. And what you did is you took a normal distribution, you took the standard normal, you divided by the square root of a chi-squared divided by its scale parameter. The scale parameters cancel each other, and that supposedly is a t distribution. So I'll write that down. So you have a normal 0, 1. And I divide by a chi-squared with new degrees of freedom. And if this is so this is 0, 1, so I've already taken out the scale parameter. And I divide by my scale parameter right here. This is a t. 0, 1 with new degrees of freedom. If you work through and you prove this about an independent normal 0, 1 and this, effectively, you will solve that exact same integral that we just worked out. You'll come up with the exact same thing. So it's no different. Our interpretations are different. So when you can align, you're thinking about this and this answer, recognizing it's mathematically the same thing, but the interpretation is different, I'll think you get a lot of stuff. So chew on it. Compare your notes to things you've learned from other classes with different interpretations. But the math turns out to be exactly the same. Okay, I want to move on. I want to tell you about forecasting. Are we ready for that? Let me just tell you what a Bayesian does. And we'll come back next time. I'll show you a Monte Carlo scheme for sampling from predictive distributions, and I'll teach you some more algebra and calculus. It's how to work things out analytically. But it turns out it's very easy to sample from these things if you know how to sample from the sampling distribution and its posterior. You can sample iteratively from those. You can sample directly from predictive distribution. So our goal is to predict. And I'll say, I'm going to talk about some data point. I don't get to see it. I want to predict what a future data point looks like. This is the future. And what we get to see is data. So x's, x1 to xn, where all of these xi's, and I'm going to teach you in the IID case how to do this, but there's no real fundamental difference in a non-IID case. We'll talk about that afterwards. Xi's come from some distribution, f of x, given theta. So we want pi x tilde given x. And this is very easy to get. So algebraically, it's just this. So I'm going to take my sampling distribution, If I knew what the parameters theta were, I just plug them in and I would know what that distribution is, but I don't get to know what theta is. So instead of just plugging something in, the Bayesian mixes over the posterior distribution, d theta. And that's all you do. So this is the posterior. We're going to pick up next time, starting with this. I'll show you some examples. We'll work through some math. But a Bayesian, if they don't know what theta is, they build posterior. Now it's a random variable, theta. It's conditional on what you get to see. And I'm going to mix over the sampling distribution. And that's going to give me a new distribution. We'll start out with the Monte Carlo scheme, and then I'll move this now. That's it for now, guys. Thanks very much.